Harsh Gupta is currently a PhD student at the Indian Institute of Science, Education and Research, Bhopal, India. He previously worked closely with Union Bank of Switzerland at Infosys. He left the corporate world and joined academia to pursue research in quantum information. His work focuses on measurement-based quantum computing and development of non-CSS quantum error-correcting codes. He has contributed to algorithms to generate non-CSS codes using cluster states and has studied further the behavior of stabilizers after cluster state measurements. His most recent work, fault tolerance of 613 non-CSS code generated using measurement on graph states, was also invited as a contributing lightning talk in the IISc Fujitsu 2025 workshop last month. So with this, we would like to invite Mr. Harsh Gupta. I will have to allow him. So yeah, Harsh, could you please share your screen? Yes, I can see you. Harsh, can you please share your screen?
Yeah, just a second.
Sure. Yeah, there you go. We can see your screen.
Yeah, can you hear me?
Yeah, I can hear you clearly. You're good to go.
Yeah, okay.
Yeah.
Thank you, Asif, for inviting me in this talk. And I'm really feel delighted to give the talk on measurement-based quantum computing. So, hello everyone, my name is Harsh Gupta. Currently, I am working on developing the quantum error correcting codes with the help of measurement-based quantum computing. I'm a PhD student in IISER Bhopal. So, first I will start with like what is the gate-based quantum computing, and then what is the measurement-based quantum computing, and what is the ingredients needed for the measurement-based quantum computing. For example, cluster and the gates which we need initially, and then the stabilizer formalism which we need for the measurement-based quantum computing, and how with the help of stabilizer formalism it will help us to find the quantum error correcting code with the help of measurement-based quantum computing. And in the end, I will conclude my slides with some of my work. So here in gate-based quantum computing, we already know, right? Like the qubits we have initially, and they are initialized with some states, and then we applied the quantum gates. Like here you can see Hadamard gate, C0 gate is applied, and then in the end we measured the quantum states. So the states will evolve with the help of quantum gates, and the measurement will happen in the end, and we can like track the states accordingly, like after which gate or what will happen. And so from the starting to the end we can track the states. But in measurement based quantum computing, so what happen is, as you can see here, like there are a bunch of qubits and they are connected with each other, and when we measure them, then the information will pass from one qubit to another qubit, that we will see later how it will happen. And then the bunch of other qubits, they will entangle together. So that's how, like, the basic formalism of measurement based quantum computing. So for example, here you can see like what is the basic ingredients we needed for the measurement based quantum computing. So as you can see, every qubit is initialized with plus state, and it is connected with the CZ gate. So this is the first ingredients which we needed for the measurement based quantum computing, and we call this as a cluster. So mathematically they can also be defined with the help of undirected graph, where vertices is defined the qubit and edges is defined the quantum gates. So this quantum gate is a CZ gate. So the beauty of CZ gate is the control and the target is same when we applied this two qubit gate between the qubits. So that's why it is denoted with the help of this edge and undirected graph. So as the result, the cluster states you can see here, it's like the CZ gates, which is applied on the plus states, and all the qubits is initialized with the plus states. Now, so let's take this example. For example, we have two qubits here, and the first qubit is initialized with some input, and the second qubit is initialized with some plus state, and both is entangled with the help of CZ gate. Now here you can see when we applied the CZ gate, and in the end when we measure the qubit in X basis, so you can see if we get the plus state, the output we will get on the second qubit is Hadamard times of input, and if we will get the minus state, the output we will get is like the Z and then Hadamard of input. So if we club together, in the result you can see it is like Hadamard, then Z, and then input, where this Z gate is depend on the measurement of the first qubit. So you can see with the help of measurement how the information will transfer from first qubit to the another qubit. So that's how the measurement will work. Here we are specifically choosing the X measurement only currently, because if we will choose the Z measurement, the information will die. And it's just a simple mathematics, nothing else. Like here, I break the information with plus and minus basis because we are measuring the information, measuring the qubit in X basis. And if I measure the qubit in Z basis, you can see if Z basis I measured, then there is like it makes no sense. Like nothing we will gain in the second qubit. Similarly, if we will measure the qubit in Y basis also, we will get the same results with some global phases. So now we like here we have the second qubit with plus state. We just exchange this with bunch of qubits which we defined earlier called cluster. So here the message qubit is this, and this is replaced with the cluster. Now the whole information when we measure the message qubit is encoded in this cluster. That's how the measurement based quantum computing will work, and it is how we can generate the quantum error correcting code also. So it's like the information in the first qubit is now transferred to the, like here if we will say it's like the transfer to the 9 qubits. So it's just like an encoding process. In terms of classical sense, we will say like the information is embedded in the 9 qubits. But the issue is here, like if we will write all the states in vector, but it will get huge. Like it's very difficult to track and very difficult to see what we are getting and all these things. So that's why this stabilizer formalism come into the picture, so that it will give us a very precise picture and very beautiful way to represent all the vector space. Like here we are getting some vector which is representing the states. Now with the help of this group theoretic approach, we can get it. So what we will do is we will define a group Gn, and this group is closed under multiplication, and then we define another subgroup S where every element is fixed the vector space. What is mean by fixed we will see in next slide. It's just give the +1 eigenvalue. So it's just like with the help of this example you can understand. So for example, initially we have state psi, and in that psi you can say like I think it's like I need to remove that 1/√2. You can say that it's just like alpha of 0 0 0 plus beta of 1 1 1. Then this S has these elements which is Z0 I Z2 and ZZI and IZZ. All these will give the +1 eigenvalue. So it's like every element is fixing this psi, but all we need is the generators. It means, as you can see here these two elements like ZZI and IZZ, they can generate the whole S group. So every element is fixing it, the vector space. So that's why now instead of writing psi in a vector form, what we can do, we can just write this stabilizer generators, and we can say that okay, this stabilizer generators is now representing our psi. So and after that, what we did, we converted into another mapping, which is called parity check matrix. So here, like Z is converted in 0, 1, X is 1, 0, Y is 1, 1, and identity is 0, 0. So like the stabilizer you can see here is ZZI and IZZ. So ZZI can be represented at, like, Z is 0, 1. So this is 0, this is 1. Similarly, this second Z, this is 0 and then 1, and then this is identity. So it's like 0 and 0. So it's like from one thing to another thing. So first we map the state into the group theoretic approach in, like, with the help of these generators, and then this generators is converted into the parity check matrix. So now this parity check matrix is representing our state. So if someone will give us the parity check matrix, we can say that yes, it is representing some quantum error correcting code. And now we will see how this will help us to find the characteristics of the given quantum error correcting code. But the thing is, for example, here you can see, like, it is a 4-qubit cluster with 1 message qubit. So it's like a 3 qubits which are initialized with plus states, and then we have the input qubit. We didn't measure it till now. It's just before the measurement how we can represent the parity check matrix. So this beautiful way, like, it is given by Chine et al. In 2017, where what you can do is, if you have a cluster and with message qubit, then you can simply write in this form, where first is the identity element, then this is a null vector, and then this is an adjacency matrix of the cluster without the message qubit, and then this is ACM, which is called the check nodes. So like the message qubit is connected with, like here you can say the message qubit is connected with 0 and 2. So like the last column you can see here, it is connected with 0, that's why it is 1, and then it is connected to 2, then it is 0. Similarly, like if you break down this matrix, let's say the first half, we can say this is the identity element here, and then the null vector. And then the second is the ACC, which is called the adjacency matrix of the cluster, and then the ACM. So now this whole thing is just represented with the help of this parity check matrix. But the issue is, when we measure the information, our state will change. So when our state will change, it means our stabilizers will also change. It means our parity check matrix is also changed. So we develop an algorithm, and actually this method is already known, but it is known in terms of operator picture only. Like in terms of operator picture means, like, for example, if someone give us this stabilizers initially, and when we measure the cluster, then how the stabilizer will evolve from S to, let's say, S dash. So what we did is we mapped this, and we saw, like, if we someone give us the parity check matrix, and let's say someone measure it, then if S is changed to S dash, then similarly how the H is changing to H dash. So it's just the mapping which we did in linear algebra. So like, for example, here you can see we have the 7-qubit code where we measure the message qubit. So what we did is, initially, like, it is the ACC ACM kind of. Similarly, like the identity element is here and the null vector, and this is the ACC, like the adjacency matrix of the rest of the cluster, excluding the message qubit, and the check node matrix, where the message qubit is connected with all the other qubits of the cluster. Now, when we measure the message qubit, what we did is, like, algorithm, like, you can read it, this paper, and get it in details, but in a layman terms, what we will do is, we will first make this column an identity column. Means the first term is 1 only, and the rest of the terms we will get into the 0. So what we will do is, we will add this row to all the other rows. And in terms of operator picture, what we like, this row is representing the stabilizer, one of the stabilizers. So it's like just one of the stabilizer is multiplying with the other stabilizers. But in matrix, it's just like the one row correspondingly give the modulo 2 row operation addition with the other rows. And when we did that, then what we will do, we will measure this message qubit, right? So when we measure this message qubit, it means there is no need of the message qubit. So there is no need of the stabilizer, which is representing the sixth message or seventh qubit. So here, that's why we remove this columns and then we remove this row also, because it is anti-commuting with this measurement which we will did in X basis. So the rest we will get here is the parity check matrix, which is representing our encoded message. Like here, we saw just after the measurement, when the message got encoded, we got this state as we see here. So for this, we have get the parity check matrix. Similarly, here we get the parity check matrix. So now, while measuring it, what we will do is we simply apply this algorithm, and it's just a, and accordingly we will get this parity check matrix, and then we analyze this matrix, like how we will get the quantum error correcting code, how it will help us to find the parity check matrix. Similarly, while what you can do is we can go in the reverse way. Means if someone give us the parity check matrix of the stabilizer, like the quantum error correcting code, and we have the stabilizers, and then we know the parity check matrix of this, can we go in the reverse way and find the cluster which representing it? So we also made it in a reverse way also. So with the help of this, what we find out is this 613 code. So what is happening here is, for example, we have the cluster, we have the message qubits, and then we want to find the syndromes of the qubits. So while measuring the syndrome, if we'll get an error in the syndrome, then the error will transfer from message qubits, from the syndrome qubit to the message qubit. So while getting this, so this code was, I'm saying this code was discovered in 2017, and what we observed is they just provided this code 713 code, nothing else. They just said, okay, we have this code, and while we are doing it, we can make the code fault tolerant, because when you measure the syndrome, the error will like pass from syndrome qubit to the message qubit, then we can identify it. So what we observed is, okay, and we saw, okay, we can make the cluster for those codes, and similarly we can find this 613 code, which is the most optimized one, and it is called as the Bayer code. And after that, we did the analysis on this code analysis we did, and with the help of this code analysis, what we find is, like, our code is performing almost same as this 713 code for the anisotropic noise. And then yeah, that's it. I think that's what we did. And so one of the key takeaways, what we did is, for example, they only just provide the 713 code and 813 fault tolerant Bayer codes, and then we optimize this to the 613, which is the most optimized in terms of fault tolerance for the anisotropic noise. It's just particular for the anisotropic and the depolarizing. And previously they didn't provide any construction for that. Means they just give the code and they analyze it, and they said we find those code with the help of some greedy search and all. But now with the help of graph-based approach, we can say that, okay, at least we have some search space where we can find those code and we can do the analysis, and maybe we will find some other codes also. So it's just a area which I am working on currently. Yeah, thank you.